Okay, we talked about blood gas analyzers. We do 1 and 2 point calibrations. We use PO2 and CO2. We also have electrolyte solutions. We have controls that will have a pH that is a certain thing, and a CO2 that should be a certain thing, a PO2 that should be a certain thing. Solutions that go across as they're analyzing, as they're calibrating to test their calibrations, also occur inside a blood gas machine. Blood gas machines are getting pretty darn sophisticated. A lot of the work that we used to have to do as respiratory therapists to make sure that they stayed calibrated, that they got the 1 point cal, they had the 2 point cal, that they calibrated and came in, and there was no drifting that went on, and that the quality controls are all within the right range, has come so sophisticated that really, as an RT, a lot of times you don't have to do a lot. The machine does most of the work for you. However, with that being said, there's always going to be somebody out there who's monitoring these things and making sure that that linearity is staying as it should, making sure that the controls are doing what they're supposed to do. That's just the nature of the beast. We did talk about controls. There are different types of controls that you can use. You can have on a blood gas machine blood-based controls. You can have water-based controls, or you can actually have what's called a fluorocarbon. Typically, you will do a 3-level of control on a blood gas machine. You'll have something that is acidotic, you'll have something that's normal, and then you'll have something that's alkalotic. I don't see that on here. It must have gotten knocked off, but alkalosis should be the 3rd level. This is referred to as a Levi-Jennings chart. A Levi-Jennings chart is basically monitoring and looking at linearity, okay? More of a horizontal linearity versus an angled linearity. The first chart, the top one, will show you where you have a blood gas pH that's ranging between 7.38 and 7.415. And anything in between those 2 dashed lines will show you that they're within the standard deviation. It's acceptable. They're pretty linear. Now you'll find one that falls outside of the acceptable, the linear range, but still is within the acceptable standard deviation. That's just a variant that happens on occasion. Now if you go to the middle chart, we look at the PCO2 that we're measuring on this particular chart, and we'll notice that for the first several runs, it was within the range that was acceptable of 37 to 43. However, there's a lot of swinging going on. I mean, this would concern me because it's kind of all over the place. And then if we look at run number 8, it exceeds the +2 standard deviation. That means that if it exceeds it, it's something that you need to address. It's an outlier that needs to be addressed. It was out of control on that particular run. So that means either you need to recalibrate the machine, you need to look and figure out why it was out of calibration, and then rerun that control before you run any actual blood gases on the machine. Now if we look at the last one, which is PO2 control, the acceptable range is 96 to 104. We started okay. We have one that was high but still within the standard range, and then notice what we see. We see a trend. It's trending out of control. It's consistently dropping. It's showing a pattern. You need to be watching for those, and ideally you catch those and try to fix them prior to them actually getting out of control. Just because it's within that ±2 doesn't mean that you don't necessarily have to do anything about it. If you've got one that's an outlier, not a big deal. But if you're seeing a trend, you need to address it. The moment it becomes out of control, or if you see this trending too out of control, you need to figure out what's going on and not run any more blood gases on that particular machine until you've addressed it. You know, blood gases machines have a lot of maintenance, especially the older ones. They have little membranes that dry out or various things that can occur that you may have to readdress. Fortunately, the newer machines have these cartridges that have all these pieces in them that typically don't dry out because you pull it out, say, every 30 days or whatever and dispose of it. And so that maintenance is much better, a lot less work for the RT today. your DLCO analyzer, we're using carbon monoxide, so we have to have a carbon monoxide analyzer. We're not using a lot of carbon monoxide. It's very minute, but it's just enough. And then we have the tracer gas analyzers. And the tracer gas analyzers, it's like a helium or methane that's used to kind of track and help keep up with what the CO2 is. Body plasmography, we use a lot of pressure. And we look at the pressures when the door is open, the pressures when the door is closed. There's manometers that you got to do. You have to know what the barometric pressure is. You have to know what the box pressure transducer is. When we go to Colby to play with their machine, as it's calibrating, reach and push on the glass. It'll throw the entire calibration out of whack because you just increased the pressure on the glass on the outside of the box, and it changes everything when you do that. That's kind of an interesting little thing. You can see it immediately occur. Flow transducers, we want to use that sine wave pump that we talked about earlier. We can also use what's called an isothermal lung analyzer. And what an isothermal lung analog does is basically it uses copper to simulate the typical compliance that you would have in the alveolar structures of the lung. And then it can measure the volume and pressure related to something that's not changing. It's the glass kind of holds it consistent, but we actually have the metal in there that can mimic the alveolar structures and determine and adjust and do calibrations based on that, rather than some test lung out there that doesn't have those properties in it, so it's really not going to have similar compliance issues that we have in the lung.